All right, welcome back, everybody. Today we're going to be doing section 15.4, which is all about applications of double integrals. So the past couple sections, we developed the double integral. Now we're going to use it for some very specific applications, namely some physics and engineering applications. Let me go ahead and pull up the slides and we will get started. There we are. Okay, so a couple of things. Here's the overview. We're going to start by just recalling the fact that the integral is kind of our canonical measuring device. Then we're going to talk about density and mass. So if you remember when you discussed these concepts back in, what was it, Calc 2? Calc 2. It's kind of a repeat of those sections, or that section, except now it's with higher dimensions, right? So 2 dimensions in this case. Then we'll talk about moments and center of mass, moments of inertia, and we'll finish up with the radius of gyration. One note that I want to make here is that this section actually includes another very important application, which is the one on probability and expected values, but we won't be covering that in this lecture, unfortunately. But I encourage you to read that section. So you should read that section or that subsection on probability and expected values, just because I don't want to say one of the main uses, but all of the interesting probability problems out there are related to calculus, and you need multivariable calculus to get into the more interesting problems. So any of you that are interested in probability and stats, or if you want to become an actuary someday, or you want to become a risk analyst, I encourage you to read these subsections on your own, and then you'll have a little bit of a leg up when you take a probability and stats course later on in your undergraduate program. All right, so let's start with this. So if you remember, the Rees-Markov-Kakutani representation theorem kind of tells us that our integral is like our canonical measuring device. So if you have a linear functional, then it basically can be described in terms of a Riemann integral using an appropriate measure. So the moral of that idea is just that if you want to measure something, you're almost always going to use an integral. And that's why we study the integral. And that's why we have, whole books dedicated to the integral. So we've already used it before to measure things like arc length and volume. Oops, that should say and. Arc length, or that should not even be there. Arc length and volume. And in this section, we're going to use it to measure things like density, mass, or I shouldn't say density, but mass and moments and things like that. Um, so you might remember from Calc 2, you were able to find the center of mass of a region, or they called it a lamina, that had a uniform density. That was one of the assumptions that we had back in that section. At that time, it wasn't possible to use the tools yet if the density varied depending on where you were in the region. But now that we have the double integral, we can account for that. So one of the assumptions previously in Calc 2 was that the region that you wanted to find the mass of basically had uniform density. Because if your density is not uniform, then you have to assign a different value based on your location in the actual region, right? Now we can do that using multivariable functions and multiple integrals. All right, so here's the setup for density and mass. Suppose that a lamina occupies a region D of the xy plane, and we're going to describe its density at the point x comma y, and we're going to denote the density function with rho. So rho of x comma y is basically the density of the region at that point. And we're going to assume that rho is a continuous function on D. So more precisely, what we're saying is the way that you define this density function is through this limit. And what that limit is doing is it's basically taking the mass and dividing it by the area. When you start by looking at like a tiny rectangle, so you'll see this theme over and over and over. You look like at a tiny rectangle, and then you let the rectangle, the edges of it, shrink to nothing. And the limit of that is rho of x comma y. And we're assuming that it's continuous. So not only does that limit exist, but it's actually equal to the number of the density at that point. All right. Okay, so that's the initial setup. Now, if we want to find the total mass of the lamina, then we're going to do something that we did similarly in section, what was it, 15.2, and then kind of again in 15.3, and then we're going to see it again in 15.6 and 7 and 8 and 9. But we're going to take our region D, we're going to enclose it in a rectangle, and then we're going to use an indicator function to basically define our density as 0 when our point is not in the region D. That's what the indicator function does. It basically says, yes, you are in the region, or no, you're not in the region. Then we're going to do this classic technique. We're going to partition the rectangle into KL subrectangles, R sub ij. And we're going to choose a sample point, x sub ij star, comma, y sub ij star in each one of these rectangles. And then what we can say is that the mass m sub ij of the part of D that is in each one of these subrectangles is about this value here. So really what we're doing is we're taking the density and multiplying it by the area, and that gives us the approximate mass. That's basically the idea. So then what we're going to do is we're going to add up all of these values over every single one of these little sub rectangles. And when we add them all up, we get an approximation of the total mass of the region D right here. All right, so that's the setup. It should be very familiar. We're going to see it over and over again, but you basically have this function, you have this this differential here, or sorry, you just have this value here. And then when we take the limit as the partition gets more refined, we get a double integral. And this is what we're going to call the the total mass, sorry. So taking the limit as k and L go to infinity, we get the definition of total mass, and it is this double integral right here. All right? Okay, so let's try to find the mass in this example. So let's say that we have a charge distributed over the triangular region shown below here, and we're going to define the charge density in that region based on this function here. So the charge is x times y, measured in coulombs per square meter. And the question is, what is the total charge of the region? So this is one that I do want you to try on your own. So first thing is just read it a couple of times, think about it for a moment. Okay, and now the good old verbal, right? Verbal cues. So speak out loud to someone or no one, to your wall, to your dog, to anybody, just to give your brain that verbal feedback, that audio feedback. That'll help you kind of make sense of your ideas. All right, now try to work it out on your own using the formula that we just derived for the total mass of a region, and then we'll do it together in a moment. All right, here we go. So we've got our density function, and we've got our region, and we're pretty much just going to do a double integral. We just have to remember that we have to tell the integral how to scan the region. So this is the way that I chose to scan it. So what I'm doing is I'm going to differentiate. I'm going to integrate with respect to y first, and y goes from this lower bounding line to this upper bounding line. So y is going to go from 1 minus x to 1, and those are the bounds of our first scan, right? Then after we've done that, we're gonna let x go from 0 to 1, and that'll complete the scan of the whole region. So that's where this integral is coming from. Oh, one thing I should point out, we are able to iterate this integration because this function is continuous. So you remember Fubini's theorem basically said if you're continuous, then you can iterate your integration process. Technically on a rectangle, but that's why we had the indicator function to take care of the zero areas. All right. Now we're just going to use FTC1 on y. There we go. So the antiderivative of y is 1/2 y squared. Evaluate, then we're left with just a function of x. Okay, and then we're going to simplify that and then use FTC2 once more. So we end up with this lovely polynomial here. Use FTC2 again, and then in the end we have that the total charge of the region is 5/24 coulombs per square meter. Not too bad, right? Pretty straightforward. Okay, so now that we have a handle on total mass, now we can talk about moments. So if you remember from Calc 2, we derived some formulas for the center of mass of a region that had a uniform density lying under a curve y equals f of x. And the formulas that we came up with are these right here. So the center of mass is m sub y over m, and then it ends up being this integral. And then the center, sorry, this is the x coordinate of the center of mass. And then the y coordinate of the center of mass was given by this formula here. If you're curious about a detailed derivation of those formulas, I did record a lecture on it, but I cannot recall the section number off the top of my head. Give me 1 second. I can look it up real quick. Section 8.3. So if you go to my my Math 8 lecture series, it's section 8.3, and that's where I go through the full derivation of these two integral formulas right here. So m sub x is the moment of the system about the x-axis, and m sub y is the moment of the system about the y-axis, just as a reminder. Also, you can recall, and I go over it a little more in that lecture, section 8.3, that a moment is just the product of a particle's mass and its directed distance from an axis. So for example, this and this right here. Okay, so now here's how we're going to set this up. We're going to do the same technique. We're going to use our subrectangular decomposition from earlier. The moment of the part of D that is in a subrectangle with respect to the x-axis is approximately this value right here. This value right here. And remember, because we're taking the distance from the x-axis, this distance is actually y. So that's why you have the variable y there. Even though we're saying it's with respect to the x-axis, the reason that it's y is because this is where we're measuring from, this is where we're measuring to, and so the distance is actually in terms of y. That's why that's there. And then you just have the mass, right? So remember, mass is density times area, or density times volume, right? So that's what's happening right here. That's the m sub ij. Now, add up all of those individual moments of every single little subrectangle, and then you take the limit as delta A goes to 0, and you get the following definitions. Here we go. I kind of merged them into the same thing just because the construction is very similar. So the moment with respect to the x-axis is given by this double integral. And it's just like an infinitesimal version, or this is like an infinitesimal version of the area, right? But the formula is the same. So we're basically taking the mass, this is the infinitesimal mass, and multiplying by the distance from the x-axis. That's really what's happening. And then the moment with respect to the, ooh, wait, do I have these backward? Sorry, that's a typo. Let me fix this typo here. That should say y-axis. There we go, yeah. I'll fix that after the recording. So then the moment with respect to the y-axis is the same idea, except now our distance is x, kind of for the same reason, right? If I go back, if we want to measure from here to here, then the distance is actually in terms of x. So that's where this is coming from. All right, so now we have our moment formulas, and now we can talk about the center of mass of this region. So the coordinates, or really I should say the point, this is the point x bar comma y bar of the center of mass of the lamina occupying the region D, having density function rho, are given by these formulas right here. There it is. So very, very similar. You're basically just taking this and dividing it by the total mass, just like we had done earlier with when we had what was it? A region that had uniform density. And what is the total mass? Well, the total mass is just adding up all the mass of the individual subrectangles and then taking the limit as the area goes to 0. All right, so that's the idea. These are formulas that you really should memorize. So do memorize these formulas. I won't provide these on the test, but again, they're not too difficult to remember. You know how I feel about memorization. Try to memorize as little as possible. You should be able to understand the construction of these things deeply and intuitively enough that you could kind of just figure them out on the fly. Again, I mean, this is just distance from the y-axis, and this is the mass, right? So you're adding up the moments and dividing by the mass. Kind of the same idea. Okay, now let's practice. And this is one that I do want you to try on your own first. So let's say that the density at any point on a semicircular lamina of radius A is proportional to the distance from the center of the circle. Find the center of mass of that region, that lamina. All right, so first thing is think about it for a minute. Maybe just read it in your head a couple of times. Right? Now say something out loud to give your brain that feedback. I haven't said this before, but I really should. You could even just read this sentence out loud to yourself a couple of times. Read the question out loud over and over and over again. That's a lot of what studying math is like. You just keep repeating it over and over out loud until it makes sense. Okay. And now try to work on it yourself. Try to find the center of mass, and then we'll do it together in a moment. All right, here we go. So we need a way to describe the disk. That's the first thing we need to do. So we can describe the lamina D as the upper half disk. So basically this is a full disk of radius A, but we're just going to take the upper half of it, right? So the distance from a point in this half disk to the center of the circle is just given by the good old distance formula, right? So as a picture, you could think about it as, do this, And then this is a, this is negative a. So pick any random point in this little semicircle, and what's the distance from that point to the center? It's going to be the square root of x squared plus y squared, just by the distance formula. So if this is the point x comma y, for example, that's really all we're doing here. Now, because it says that the density is proportional to this value, that means we're going to multiply this distance by some constant of proportionality. We'll call it k. So the density is given by k times the distance to the origin. Then this last note that I have here, the structure of the problem and the structure of the region suggests that we should use polar coordinates to integrate rather than using Cartesian coordinates. Everything is very nicely radial, so we should appeal to the radial nature of this region. All right, here we go. So using polar coordinates, this is just equal to r, and r goes from 0 to a, right? R goes from 0 to a, and because we're only looking at the upper half of the region, theta goes from 0 to pi. So that's how we can set it up. The total mass of the region is this, right? Density times area, add it all up. Our density function is given by this. And then we can iterate this. So this is something I should point out. This function is continuous on that region. So Fubini's theorem says we can integrate iteratively. And that's what I'm going to do here. So I'm splitting this double integral up into an iterated integral. And here is what this becomes. And then remember, when we change our area form from one that's in terms of Cartesian coordinates to one that's in terms of polar coordinates, we have this extra value here, this extra factor of r. So don't forget the extra factor of r. And we're going to make a lot more sense of what this thing is when we get to chapter 15.9, section 15.9. All right, now we just have an integral to evaluate. So you can use all the techniques that we explored previously. One thing I noticed right away is that k is a constant, so we can pull it all the way out. Also, this function doesn't depend on theta, so we can actually split this double integral into a product of two separate integrals, right? Using that very satisfying corollary from earlier. So here is the first integral, and here is the second integral, and we can evaluate them individually. This integral is just going to become pi. And then here we're going to use FTC2, or we're going to use FTC2 again, and we're just going to use the power rule for antiderivatives, and we get that. Simplifying, we get k pi a cubed over 3. There it is. So that's the total mass of the lamina. Now we need to find the moments, and then once we find the moments, we can divide them by the mass, and then that will give us the coordinates of the center of mass. So that's the next step. So d and the density function rho are symmetric with respect to the y-axis. So we know immediately that the x-coordinate of the center of mass has to be 0. Again, if you think of the picture, like that, we'll call that a, negative a. The way that the density is described, well, first of all, I'll say this. The region is symmetric about the y-axis, so it's like the same on the left and the right, right? They're like mirrors, okay? Maybe not the same, but they're mirrors, right? Now, the density function is actually kind of reading like something that has this shape, right? Because the density is proportional to the distance from the center. So because that region and the density function are symmetric about the y-axis, we know for a fact that the center of mass has to lie on that line, which is the y-axis. And what is the equation of that line? It's when x is equal to 0. So the x coordinate has got to be 0. So that means all we really need to compute using integrals is the y coordinate of the center of mass. So here's what we're going to do. Here's our moment integral right here, distance from the x-axis. And then we already found the mass. So 1 over the mass is just the reciprocal of the mass. Same thing as before, this function is continuous on that region, so we can iterate our integration process. This is the function we're going to integrate. And just like before, this is actually a product of two disjoint functions of two different variables, so we can split it into a product of integrals. So here's the first integral, and here's the second integral. Run FTC2 on both of them separately. You get that? You get this as a result, and then you can simplify to get 3a over 2 pi. So that is the y coordinate, somewhere in here. somewhere in there, but not perfectly in the center. That's the point. All right. Altogether, we have the center of mass is at this point. So these are the coordinates of the center of mass, and that's where you would basically place your finger if you wanted to balance it. So if you had, if you had this thing and you wanted to balance it on your finger, this is where you would balance your finger. That's where you'd place your finger to have it balance, like so. All right. So now that we've got that, we can talk about the second moments. So the second moments are the moments of inertia. And the moment of inertia of a particle of mass m about some axis is defined to be mr squared. So mass times radius squared or distance squared. So r is the distance from the particle to the axis. So our second moment formulas are really very similar to our first moment formulas, except now it's going to be squared for those distances instead of just single, right? So you can go through the entire derivation again. You could talk about the region D. You can construct the Riemann sum. And then here's our squared distances, right? And then take the limit as the partition gets more refined, and then you get this double integral. So the only difference at this point is that this is now squared, and this is now squared. Not too bad, right? Okay. So not only do we have a moment of inertia with respect to the x and y axes, we can also talk about the moment of inertia with respect to the origin, and that's what we're going to do next. So the moment of inertia with respect to the origin, or sometimes called the polar moment of inertia, is again constructed the same way, except now what you're going to do is you're going to take the distance to the origin. So the distance to the origin is just the square root of x squared plus y squared. But because we're doing the second moment, so r is the distance, right? We're doing the second moment, the square root and the square are going to cancel, and we're just left with this. There you go. Take the limit as m and n go to infinity, and you get the actual double integral for the second moment with respect to the, I'm sorry, the moment of inertia with respect to the polar, the origin. My gosh. Mixing up all of these things. There you go. All right. Here's all three of them. Again, these are formulas that you should memorize. They shouldn't be too difficult to memorize. They're really just the same as the formulas for the first moments, except now these factors are squared. And then one thing I wanted to point out is that I want you to notice that the moment of inertia with respect to the origin is really just a sum of the moments with respect to the axes, like so. And that's because of linearity of the integral. So quite literally, if you take this integral and you add it to this integral, you will get this integral because the integral is a linear operator. Okay. All right. Now, here's another one that I want you to try on your own first, and then we will do it together. So here we go. Find the moments of inertia of a homogeneous disk D with density rho equals rho, center at the origin, and radius A. So one thing I want to say here or mention here is that here our density function is uniform. So the density does not depend on your location in the region. It is a constant. So the density is fixed, all right? Okay, so think for a minute about how you would approach this. And then, as always, say something out loud to give your brain that boost. And now try to work it out on your own. Find the moments of inertia under these conditions. All right, here we go. So, yeah, so this one, we're actually going to do the moment with respect to the origin first. So the boundary of D is the circle x squared plus y squared equals a squared. So the polar moment of inertia is actually really quick and easy to calculate. This is just going to become, wait, r squared, oh yeah, r squared times r dr d theta, right? Because rho is just going to be rho that pulls out. This becomes r squared. And then here's that extra factor from when we changed to polar coordinates, right? Once again, this is the functions of theta and r are disjoint, so we can split this integral up into a product of two integrals, run FTC2 twice, and then we get this. So that's the polar moment of inertia. Now we're going to find the moment of inertia with respect to the x-axis. So that's I sub x. It's going to be y squared times our density. And then the setup is very, very similar. We can pull rho out of the integral because it's a constant. It's not going to change depending on where we are in the region. We get r squared sine squared theta r dr d theta, right? Now we can split this up. So, actually, hold on one second here. Did I do this already? You see, so that one, r dr. I could have, wait. Yeah, I could have split it up. Yeah, I could have split this one up into two separate integrals, but I guess I didn't here. These are still disjoint. So like this function here, and then the factors involving r are disjoint. So you could split it up into two separate integrals. In this case, I didn't. I just worked from inside to out. So I integrated with respect to r first and got this. Then I'm going to integrate with respect to theta. So this is the next integral that you'd have to evaluate. One note I will make here, this is one of the reasons why I said that you really do need to memorize those 6 trigonometric identities. There are about 6 that you need to have ready to pull out of your back pocket at any time whenever you're doing calculus and integration. I don't have those 6 on hand right now, but geez, where do I first introduce them? Oh man, I talk about them in every class. Da, da, da. I think if you look back at my, yes, yeah. If you look back at my lectures from Math 8, from Calc 2, section 7.2 is where I give a reminder of what those formulas are, those 6 trigonometric identities. And those 6 are the ones that you should have memorized so that they're easy to use in Calc 1 and 2 and 3 and beyond. All right, anyway, back to this. Polar moment with respect to the x-axis, or sorry, second moment with respect to the x-axis is this, all right? And now we can actually find the moment with respect to the y-axis by using this equation here. So because the polar moment is the sum of the moments with respect to the axes, the moment of inertia with respect to the axes, we can just subtract, and we get this, which is this. There we go. And again, the reason that you're seeing this type of, sorry, not that, the reason that you're seeing this symmetry here is because the region and the density function are symmetric, just like we saw before. So that's coming out of the actual region and the function. All right. Okay. Wait a second. What was the next thing? Moments. That's right, that's right. I have an extra note on this one. I forgot about this. So in this example, the mass of the disk is equal to this. It's just the density times pi a squared, right? So the polar moment inertia actually simplifies to this right here. And this actually shows that that moment of inertia is going to increase if we increase the mass or if we increase the distance away from the pole. So this is kind of it's gosh, what am I trying to say? Oh my gosh. This behavior that you might have seen before in like a physics class, this is why that's happening. So you can see it coming out through the actual integration process. Right. All right. So last thing we have to talk about is the radius of gyration. So the radius of gyration of a lamina about an axis, or it's often called the gyradius, is the radius or the distance r, such that mr squared equals I, where I is the mass of the lamina, I'm sorry, m is the mass of the lamina, and I is the moment of inertia about a given axis. So in other words, what this is saying is that if you concentrated all of the mass of the lamina at a distance r away from the axis, then the moment of inertia of that point mass would be the same as the moment of inertia of the system. That's basically what it's saying. So if you could concentrate everything at this distance away, then this would be the moment of that point. All right. Okay, so here is the definition. So what is the radius of gyration? The radii of gyration with respect to the two axes are denoted by x double bar and y double bar, and they're given by these formulas. So it's just kind of the same formula as before, but now this is the r squared, and this is the r squared. And then what is this point? The point that I was describing earlier, it's just those right there, which is Ix over m and Iy over m, where m is the total mass of the region. So this is the point that I was talking about just a moment ago, where if you would like concentrate all the mass at that point, that's where it is. Okay. All right. So in the previous example, we'll just piggyback off of that one. The mass was rho times pi a squared. So we can easily compute this now because we actually already found ix and we found iy. So here we're going to get y squared, y double bar squared is equal to this, which is equal to that. And then when you simplify, you just get a to the fourth over 4. And then again, because you have some symmetry, you're going to get this. That's it right there. So the symmetry is giving you that equality right there. Yeah, just because ix equals iy. All right, so that's it. So on that note, let's play. This section really isn't too long. We're not going to talk about probability, unfortunately. So if you have questions, please do ask in class, and we'll do an activity related to it. Other than that, oh wait, I will make one more note. We're going to skip section 15.5, the one on surface area. And the reason is because we will actually recover all of those formulas when we get to section 16 point, oh shoot, what is it? 16 point, come here, come here. Mm-hmm, mm-hmm, mm-hmm. Oh my gosh, I don't remember which section it is. Somewhere in chapter 16. So somewhere in chapter 16, we're actually going to get a formula for the surface area of a parameterized surface, and we'll recover all the stuff that we would have learned in section 15.5. Oh, it's 16.6. There it is. So in section 16.6, we will cover everything that we would have learned in 15.5 plus more. So I'll end it there. I'll stop rambling. Thank you again for listening, and I'll see you next time.